Welcome to the Professional Machine Learning Engineer Crash Exam course. Today we will focus on Machine Learning 101. This video will provide a blueprint for understanding the fundamental concepts of machine learning. Artificial intelligence is the broadest scope, followed by machine learning as a data-driven subset, which enables computers to learn from data examples. Deep learning is a subtype of neural networks specializing in parsing unstructured data. Machine learning is divided into three learning paradigms. Supervised learning uses labeled examples, unsupervised learning detects patterns without labels, and reinforcement learning uses positive and negative reinforcement to complete tasks. The ML process begins with problem definition and data engineering, including extraction and preparation. This leads to model engineering for training, troubleshooting, evaluation, testing, and tuning. Finally, MLOps covers model serving and monitoring. Raw data is split into the training set to optimize the model, the validation set to adjust hyperparameters and prevent overfitting, and the test set for final results on new, unseen data. Be aware of data leakage and training serving skew. A neural network consists of input, hidden, and output layers. Each neuron combines input values using weights and a bias, then applies an activation function to produce an output, introducing nonlinearity. Flow typologies include feed-forward networks, which move information strictly forward, and recurrent networks, optimized for sequential data. Scale typologies are wide networks for memorization and deep networks for generalization. Combining both creates deep and wide networks. The bias-variance trade-off illustrates model performance. Overfitting, or high variance, results in good training but poor test performance. Underfitting, or high bias, means poor performance across the board. The ideal state is low bias and low variance. To combat overfitting or improve generalization, techniques include early stopping, dropout, max norm, data augmentation, L2 ridge, and L1 lasso. The optimization engine finds the optimal answer by minimizing loss. Gradient descent calculates the slope to find the optimal weight. Backpropagation efficiently calculates the gradient. Key variables include epoch, optimizer, learning rate, converge, and batch gradient descent. For classification metrics, a confusion matrix helps visualize true positives, false negatives, and true negatives. Common metrics derived from this include accuracy, precision, recall, and F1 score. Regression metrics measure mean squared errors for continuous values, such as MAE, RMSE, and RMSLE. Raw data is split into the training set to optimize the model, the validation set to adjust hyperparameters and prevent overfitting, and the test set for final results on new, unseen data. Be aware of data leakage and training serving skew. Bias has three faces. Math bias is the intercept b in the equation y equals wx plus b. Prediction bias is the difference between the average of predictions and actual labels. Ethics/fairness bias refers to unintentional unfairness baked into the algorithms or training data. The MLOps ecosystem involves various personas. Product managers define the problem. Data analysts and engineers handle data. Data scientists build and train models. ML developers integrate models, and ML engineers operate and monitor models in production. Key concepts for data transformation include embeddings, one-hot encoding, and normalization. Architecture and scale concepts involve tensors, feature stores, ensemble learning, and neural architecture search. Remember the core equation: inference equals scoring equals predictions.